All right, good morning, good afternoon, everybody. Thanks for attending our monthly webinar series. Today, we're going to be discussing selecting and sizing odor control solutions for municipal applications. Presented today by Anthony Yamini. Anthony's been with Pure Air and now part of Clean Water One. I'll let him do his own introduction. But before we get started, a couple of housekeeping. We are going to be issuing a certificate of completion at the end of this presentation, actually tomorrow. That should come via email directly from GoToWebinar. If you have any questions, reach out to me directly. My name is Mike Dell'iacono, Director of Marketing here. I'm the one that sends you guys all the fun emails. And I appreciate you guys all attending. This next month, we will be doing in March, we'll be doing a webinar on polymer systems, sizing, maintenance, and design of that. So stay tuned and be on the lookout for an email from me. Enjoy today's webinar. I've listened through it yesterday, so it's a good one. I'm going to let Anthony take it from here.
All right. Thank you very much, Michael G. And again, thank you, everyone, for taking the time out of your busy schedules to join this webinar. It's very much appreciated. And I trust that this information in this webinar will be very helpful and useful and provide some great insight into selecting and sizing odor control systems. So with that, again, my name is Anthony Yamini. I am the Vice President of Sales and Business Development here at Pure Air Filtration at Clean Water One Company. I've been with Pure Air now for 19 years, walking down the 20-year path now. So got some nice longevity with the company, and I've done a lot of great things and had a lot of great fun in this industry as well. I have over about 25 years experience in the wastewater gas phase filtration industry itself. And my background, just a little background about myself. My background is mechanical engineering, so I gained my experience in the gas phase filtration industry designing odor control systems early in my career. So I had a great time, great insight on providing and designing these systems, mainly municipal, but also in some of the other arenas as well. I would say within the last maybe 5 or 6 years or so, I've been introduced and getting a better understanding of biological and chemical scrubbers as well. So kind of looking forward to speaking on the design considerations for different odor control solutions and ultimately what's going to be the best solution for the customers and clients out there. So in this presentation, it should be a very informative presentation. I'm very excited about it. Just kind of introduce just municipal odor control and kind of talk about that, have a brief introduction. I really want to talk about, some of the gases that are present in the municipal space and, where the overall space as a whole and kind of where those gases may be present or the systems or how they're delivered. Talk about some of the detection methods to finding out what gases are present. And then we'll start diving into the odor control technology and sizing. So you have different types of systems that can be provided depending on the parameters and the characteristics of that particular project or application. And then we'll talk about a little bit about the selection criteria and comparisons. So before we get into that, I want to do an audience poll and want to stay here. What best describes your role at your current company? All right. So I see, I'm looking at the poll now. So we have about 67% engineers. Awesome, welcome. We have some wastewater water operators. Everyone welcome. Some others undefined, but it's awesome. Great to see the attendance here for this webinar. So greatly appreciated. And I think the information that we have here should be quite beneficial and helpful. There we go. So just briefly, so before we get started with the webinar, I just wanted to highlight some of the terms that we'll be using during this webinar itself. So although a lot of these terms are used in my everyday vocabulary, it was brought to my attention that that may not be the case for others in this webinar. So just want to make sure I'm being respectful as far as some of the terms. For example, CFM, you'll hear that term used quite a bit. That stands for cubic feet per minute. So that is that flow rate for a system that's required to move the air through the system. We'll talk about ppm, which is parts per million. That's the concentration level of different gases. ACH, air changes per hour. So that means how many times will that air in a space change over per hour. So we use different numbers based on different criteria. MW, molecular weight. So that's important to know, like the weight of the gas. We use that for calculating, how much gas we'll see in a particular process, and in turn that will allow us to know how much media is required or what type of process would be best to provide a great and effective solution. EBRT, empty bed residence time. So that is the amount of time that gas is going to come in contact with that media or that solution or source to remove the different gas. And then we'll talk about FPM and feet per minute. So that's the velocity through a system. So that's important to know having the proper velocity, because that's directly tied into empty bed residence time. I will say just a quick story, talking about military abbreviations and why we wanted to highlight these terms that we're going to use. So a great friend of mine, her husband was in the military, so he would always talk and use different military terms and abbreviations. So when he did that, she would always say LMNOP, and then he would realize, oh, I'm talking abbreviations again, so I need to. Most people in the military don't understand, so it kind of slowed him down. So he actually explained what it was. So we want to make sure we did that here as well, just to explain some of the terms we'll use if they're not very familiar with everything. So for municipal odors, so there are many processes that may cause odors in the municipal world. And these odors, they can be generated at the collection systems or at the plant. So, it's going to be important for us to understand, and we'll kind of touch on it in the next slide as well, just highlight some of the most common gases, but also at each location, it may have different challenges that may affect, okay, what would be the best solution? That could come down to space or any space restrictions, site restrictions, or accessibility. So for example, at collections, say lift stations, pump stations, et cetera, or also have force main, gravity sewers, and manholes. All those areas are going to have some type of odors depending on the process. And in general, the odors are going to be the same. You have the most common culprits, such as hydrogen sulfide, maybe some VOCs, mercaptans. But what can be challenging is, depending on those levels and concentrations, well, where do you put the system? Or how can you fit the system to fit? Maybe it's a tight space or it's not easily accessible. And you have to get creative on deciding, what's the best system for that application. Same with plant odors as well. So you have, whether it's headworks, dewatering, belt press, et cetera. There are just many processes, in that facility. This has a great hand in creating different odors. And I definitely want to talk about on some of the next slides here, just what are some of those common gases and how do we treat them. So before we get to that, so just some concerns and considerations that you want to keep in mind. So each odor control application is going to be unique. You're not going to have just one, the same situation or same parameters as the next system. So you really got to take a look at the total odor removal, odor control needs to look at that. You're not just considering H2S. Because as I mentioned, H2S, always brings friends along with it. So there's going to be something that's there besides H2S, whether it's some VOCs, mercaptans, reduced sulfur compounds. So with that, what do we need to do to make sure we're taking out all of the odors? Because if you just target one type of odor, then the others are present, you're still going to get those complaints, or something's still going to be there present that's going to cause issues. So it's important to take a look at that. And we also have to allow for some flexibility as well. Because when I'm designing a system, you think about, all right, well, I know my airflow and maybe I know my gas level, or I might have to make some assumptions on the gas level, at least in the beginning stages. So we have those, have that information right away. But what about, footprint? Do I have any space? Are there any space restrictions? That could be very important to understand the best system. I may think about, well, we can use this system here. This would be perfect. But if it doesn't fit, you really can't use that. So you got to think of some creative ways to make sure you're selecting that right technology for that. So. All right, so some of the common gases in the municipal odor space. So now there's one way to figure out what odors are present, and you can just use your nose. Now, this is probably the only method right now that I would use, only area where I would use my nose if you're trying to identify something, at least in the beginning, identify gas in the beginning. So it's not very scientific, but it can give you maybe a rough idea of what's present. So for example, hydrogen sulfide, probably one of the more easy gases to detect. It has like a rotten egg smell. It also has a very low odor threshold. Now, mercaptans and some of the reduced sulfur compounds, such as carbon disulfide, dimethyl sulfide, they have more of a kind of a rotten vegetable smell, decayed vegetable smell. So, so you really just kind of get an idea once you walk onto a site. Okay, what am I noticing? So these are some of the odors. At least that gives you a start when designing the system, an idea. Now, in different odors, they're going to need different treatments as well. So that way, once you know what's there, you can design kind of the best solution. Maybe a combination of different technologies to give you that overall total odor removal. Because again, you don't want to just focus on H2S, because again, his friends come along, and he brings more than one friend with him. So we want to make sure that we are taking a look at that, the total odor profile. So now, like I said, using your nose, as well as making assumptions, can get you a good start on, okay, this is what the gases I think that are here, that I think are present. So we'll start off this solution. But at some point, when that project starts to progress, you really need to know what's in the airstream, so that way you are providing a complete solution. So, for example, maybe two people can go on the site. So one person may using his nose, may have the scent of, say, rotten corn. I've heard that before, just describing some of the reduced sulfur compounds. Whereas someone else may, smell just a beautiful aroma of putrid garlic. So which one is correct? Well, this person may smell it one way, this person smells it the other way. So, to eliminate, some of that guesswork, there's a few detection methods that we use that determine, okay, what is exactly in this airstream? So it's important to using these methods to know what you have there. So for example, the first one, if we suspect, H2S and we want to eliminate that, there's a few different devices that can be used, whether it's odor logs and acrid logs. We'll talk about that a little bit. So odor logs and acrid logs are like H2S loggers. So they can be placed in the odorous air source. Usually leave them in that place for maybe a week or 2 to 3 weeks or so. It could be longer. So what it's going to do is just log that H2S over time. So it gives you any peaks, and also give you the average H2S level over that time period. So which is great, which is very important. So at least you know, okay, what's present. This is the amount of H2S we're working with. So from there, you can at least size. That's a good start for sizing that system. Some other devices are Draeger tubes that can be used as well, and also a Jerome analyzer. Those are great for giving you that real-time information, say at the source, or if you have air movement, you can actually detect it. Detect H2S levels kind of going in and out or different locations. So it's handheld, easy to move around. Another method that that is really advantageous is taking air samples that can be sent to a lab for testing as well. So example, if a Tentlar bag It's typically used for grabbing air samples. You place this bag inside of a vacuum chamber, and you can take samples, ambient air, or also at the source, or if you have some type of system or location, you can take those air samples, send it back to a lab. They will test it for different VOCs or sulfur compounds, so you know exactly what's in the airstream. So from there, you can tailor make the exact solution for that. Now, there's some other devices that are even more advanced. For example, than a teller bag, using I call them the sumo canisters, and you can use those as well to take in those air samples. And actually, you can provide a regulator on those systems that can measure the air over a period of time. Because typically with the teller bags, you're getting a snapshot at that particular moment of what's in the airstream, versus knowing what that level is over the course of, say, a week or 2 weeks or 3 weeks. So it really gives you a good feeling for what's in the airstream. And then from there, you can determine what's going to be the best course of action. And of course, the nose is there as well. Still, the nose is useful, but would not rely on that solely in determining the system. So odor control technology. So today we're going to talk about 3 different types. We have dry scrubbing, wet chemical scrubbing, and also bio scrubbing for these systems. So all these systems are designed to remove odors, and really the project conditions and parameters is going to determine the best and most cost-effective solution for doing that. So in essence, we'll say what all these systems have in common, as we talked about the empty bed residence time, is that we need that odorless air to come in contact with the media, whether that's the dry media, the chemical scrubbing media, or the biological media. We need it to interact with that gas to remove. So that is what the end goal is, to have complete odor-free air. So let's talk about some of the different technologies. So we'll start off with the dry scrubbing from the gas phase filtration. So really the best way of looking at dry scrubbing would be 2 different types. You have adsorption versus chemisorption. So adsorption, just think of adsorbent media in that for adsorption as a sponge. So it's very similar. It's a very porous substrate, for just used for air filtration. So sort of like a sponge. So as a sponge is going to trap water, the actual media or substrate is going to capture those gases and hold them in place and not let them out. Now, like a sponge, the process using just plain adsorption would be, that process can be reversed. So as you squeeze the sponge, you squeeze all the water out, and you reuse the sponge. In some cases, you can do that with some of the medias that are used for adsorption. So whether that's medias being reused, using water to wash away the gaseous molecules that it trapped, or if you use heat to, in essence, regenerate the media itself. So you maybe heard regenerated carbons, for example. So that in those cases, it can be reused after it's reverse that process. And in also some cases, you may hear of off-gassing as well. Whereas if the media captured a gaseous molecule, we'll say a larger molecule comes in and dislodges it, or that gas goes back into the airstream. So you may have that off-gassing. So that's adsorption. And also media life, the term media life for adsorption, it can be difficult to measure because there's really no quantifiable way to determine, okay, how much media is left in this pellet itself. So chemisorption, let's talk about that. So that's the same premise where you have a media that's a porous substrate, this medium. So it's going to still capture those gaseous molecules that will come in contact with it. But the difference is that this media is actually impregnated with some type of a catalyst. So now that media is going to target a particular gas, whether it's H2S, or it can be targeting VOCs or ammonia or chlorine or a host of different gases. It's going to target that. And it's going to trap it, it's going to hold it in place, and then you're going to have a reaction between the catalyst and the gas. So it's going to turn that entire pellet into a non-hazardous, non-toxic solid that can be disposed of in your landfill. In addition to now, once that media is used up, it cannot be regenerated. It has to be disposed of. So there's no reusing that media. You have to just throw it out and then replace it with new media. And one of the benefits, some of the different chemisorption medias, depending on if they have a color to them, you may have seen some of the medias have maybe a purple color to them. That media gives you that, but that purple media kind of gives you that color change indication on when the media is being used up. In addition, some of the other medias, now that it has that catalyst in the media, you can actually measure that media life. At least in one of a few methods of measuring that life. Okay, this is a great slide. Just wanted to kind of explain a little further, how gas phase filtration works. So with filtration, really want to talk about, say, solids and liquids. This kind of give you an idea of the size of the different particles. So solids, it'd be in the form of dust or smoke. Those are about 0.03 to 100 microns in size. So typically, in those applications, something like, for example, would be like a furnace filter that you use in your home. That's going to capture any particles as that filter is saturated, take it out, throw it out, put a new one in. Liquids as well in the form of mist, you're about 1 to 9 microns as well. So you have your filters that'll capture that mist, drop it out. You can typically maybe permanent, or you can reuse them to, after you clean them, and reuse them and keep using them for a period of time. Now, gases, as you can see, are very small in size. So 0.003 to 0.007 microns. So a physical mechanical filter will not work, as those gases will pass right through it. So that's why you would need some type of substrate or media that will capture those gases. And that's where the dry absorbent media comes in. Just to give a little context, just a strand of human hair is about 50 to 70 microns in diameter. So that kind of gives you an idea of the size. Now, that would not apply to me, because you guys saw in my photo, my hair has long since departed. So, but for most, kind of gives you an idea. So, and here is a kind of example of a dry media system. We'll talk about that a little bit later here in a few slides. This kind of gives an idea as the odor's air enters. This thin band of media is being used at a time as it consumes the entire bed of media. And it's time to exhaust it out. So this is important, and there's another illustration as well showing that. So you have the contaminated air that enters the system. This media here is already spent. And then you have this thin band of media, as we call that's the active transfer zone, or the working zone. So this is where all of the work is being done to remove the odors and the gases from the airstream. And this band, it moves in the direction of airflow until the entire media bed is consumed. And then you have, of course, purified air going out. Now, this is important for gas phase and dry systems, because this active transfer zone can be monitored and tracked to know, all right, so now I know when I need to change out the media. Can I touch on that? Well, we got to, so we'll kind of touch on that, some monitoring devices shortly. But again, here are some of the activated carbons, different medias that are used for the engineered absorbents, activated carbons, and scavengers. So as an example here, activated carbon be more so as a adsorption. So it's going to capture those odors and hold them in place. Great for VOCs, not necessarily targeted gases, but it's been used for decades, and it's very effective for removing the VOCs. You have the engineered absorbents that can come in a host of different substrates and impregnates, but it kind of gives you an idea. This particular photo of a absorbent impregnated with potassium permanganate gives that purple color. That's going to be a great oxidizer for many different gases. But the engineered absorbents are designed to be targeted for particular gases. So they come in very handy. It also allows to provide a system that's going to be maybe smaller in size, and you can really affect help with any space restrictions as far as footprint as well. And then we also have scavengers. There are scavengers there that are great for like a good low cost kind of roughing type of filter or media that can be used in some applications. So I liken scavengers to as punching bags. They're going to take the brunt of the hit, and that, while allowing some of the other medias to come in and polish it up. So there are great uses for these medias, and especially in combination and conjunction, because again, we want to target all odors, not just one type. And I wanted to mention media shelf life as well. These medias, as long as they're stored indoors, I wouldn't say they have an indefinite shelf life, but they can be stored for quite a while as long as they're protected in the dry space. So that's important, in case there's any requirements to need a quick media change out, it makes more sense to have some media on hand for that. Now, for dry filter media monitoring, and as I mentioned previously, as that working zone that's going throughout the media, there's ways you can track that zone to know exactly when it's time to change out the media. So now, as I mentioned previously, when you're trying to determine odors, it was okay, you can use your nose to kind of give yourself an idea when it's time to change it out. All right, now this is one of those times where you do not want to use your nose to determine when your media is spent. Now, this is a true story. I heard a vendor who shall remain nameless, to protect the innocent, but they said the best way, they made a comment, they said the best way to know when it's time to change your media was to use your nose. So, which means that there's already breakthrough. It took me a minute to think about that. It's like, wow, okay. So I had to break that down to someone more terms that they would understand. I said, so that's the equivalent of saying, when it's time to add fuel to your car is when you run out of gas. That's probably not ideal for that. So I think it's better to have a way of predicting when it's time to change out that media versus being reactive after you have breakthrough, or for example, if you have fuel in your car stops. So it is very important for that. So I would say, and thinking about it, most processes in the municipal world are watched and monitored. So say, for example, pressure, temperature, flow. So if it's determined that particular application needs an odor control system, why not monitor the most important part of the system, and that's the media. So you want to know, okay, when is the time to change it out? So I can predict that out months in advance versus guarantee something's going to happen where you're going to have breakthrough. It's going to be on July 3rd, right before the 4th of July parade on Main Street. And that system is going to be starting to break through, and it's going to smell god awful with the beautiful aroma of future garlic and rotten eggs. That's not going to be ideal. You won't appreciate that. So, and then at that point, it's too late because there's no way any vendor could probably react and get any media there in time to do that change out. So it's important to be able to predict those changes and those occurrences versus being reactive. And that's what makes it beneficial as well. If you have a system, also maybe you have a spare set of media. So that way you can change it out from there. Okay, so sizing the dry scrubber, for example. So usually when I receive an email, someone needs, hey, I have an application, and I'm looking for an odor control system. So first information I would need is like, okay, what's the airflow? So we go back to those terms, CFM, cubic feet per minute. That's typical what we use here in the U.S., but also you maybe some different terms. I didn't get into the different airflow terms maybe used around the world, whether it's cubic meters per hour or liters per second. But so usually that information is given to us. And what's the CFM, and also in some cases then they say, oh, we already have the odor levels, which is great. And so from there, we can decide, all right, this is going to be the best, this is the system we're going to have. And we'll initially provide that. If we don't have other information as far as space restrictions, that'd be kind of the third question I would ask is like, okay, what are our space restrictions? You know, make sure that way I'm going to make sure I'm not providing a system that's going to be too big or too large. You don't want to oversize something, or of course, I definitely don't want to undersize it either. So we can kind of go from there and kind of come up with that best solution. And also knowing those odor levels will determine, okay, what's the proper velocity that I want to use as well. Now, kind of step back a little bit. If the client or someone doesn't know the airflow at the time, but if the room volume or the structure is known in that volume, then we can determine the airflow based on, you know, different air changes per hour. So we have a chart here on the side. So we have 3 air changes, you know, depending on the makeup of the room or the application, whether that space is unoccupied, could be a lift station not unoccupied, or maybe an area may be moderately occupied. You may, you know, use those different air changes for the system. Now, usually that information can be given to us, but if not, we'll make some assumptions, and we may, you know, choose a air change. We may start off with 3 and explain why we're using that. But depending on the size of our system, you know, if that air change per hour is below our smallest system, you know, and our small system has a higher airflow, and in that case, well, the minimum you're going to get is maybe 6 air changes per hour, which typically would work. It really depend on the application. And in some cases, 12 changes per hour, you have a fully occupied, say, control room, that as well. But you having that information will determine what our airflow is going to be. And then with that, once we determine the amount of air needed, then we can calculate the amount of that particular gas that's present using the formula here, or how much is going to be generated in that process. So then we can come up, because then we start looking at different systems for that. So again, in the phase velocity, FPM, feet per minute, is very important, because standard for municipal applications, you want to be around that 50 to 60 feet per minute. So, because again, that ties right into the municipal standard of 3 seconds of empty bed residence time. We want that contact time with the media and the gas to make sure we're getting proper efficiency, proper removal. And now, of course, with a smaller velocity, that means that the vessel is going to be bigger. So we have to take into account, you know, in those applications that we have the space to quite do the 50 to 60 feet per minute. So that's something we work with consultants on, and we provide the best solution for that. You know, in some cases you can go up to 100 feet per minute. We don't recommend that, but you know, depending on the application and what's required, we have some solutions that way. All right, and so some types of dry scrubbers. So again, depending on the size, the airflow required, gas level, if there's any site restrictions, footprint restrictions, that'll give us an idea of what will be the best system to use for this. So, for example, the vertical systems, just round tanks that basically blow air through the column of media and exhaust out clean air. So these are great, you know, and they come in different configurations as well, where it could be more compact, where there may be a blower that is on top of the scrubber. So it'd be great for use for lift stations, wet wells, things of that nature, pump stations. So you know, to really depend on the application, we may take maybe look at the vertical system. Horizontal systems, very similar to the vertical, except that you still have a deep bed amount of media in the systems, but that air is traveling in a horizontal fashion throughout the media bed. So starts off with a mist and grease filter capturing the moisture, goes through the system, and then here you have the 3-foot bed of media in this section here. That's going to scrub and remove all of the gases. And then typically you will have a blower section and media will exhaust on top. For the horizontal systems, they are widely popular because of the ease of maintenance for the systems. There's easy to change out. They are, can't see it on the example here, but they are equipped with vacuum ports that can be used to remove the media, spent media, quickly and efficiently. And also it's easy enough to replace the spent media through the access hatches. One of the other benefits of the horizontal style systems is that the media beds are in independent chambers. So that way, maybe if one media is not spent, but the other is, you can just change out that media without removing all the media in the system. So it makes it pretty beneficial that way. The V-bank, that's also a horizontal flow system. As the air comes in a horizontal fashion, goes through the media bed, also has independent chambers. But one of the great benefits, we're actually at both horizontal and the V-banks, is that they are low profile for one. And on the V-banks, you can go really high airflows with one system. You know, in some cases up to 40,000 CFM just with one unit. So it makes it very advantageous where I may need for a vertical round tank, I may need 3 or 4 or more of those tanks to do that. So very beneficial, but have to be mindful of footprint because the V-banks can be longer in some cases. They can be customized to be shorter, but in general, they're going to be a little longer. And then you have radial flow systems. They're also high airflow systems, but in a round configuration, but the air actually moves horizontally through the scrubber and exhaust out through the stack here on top. So great for higher airflows, same with the V-bank, except, in some cases, the footprint restrictions, footprint's very tight. And then you may have to, that's where the radial flow may come in handy because of the little more compact design. Here's just to give a good kind of design consideration example of a project. This one here was in Ottawa, Canada. So this was an application. It was 3 V-bank systems. And actually, they had multiple different gases that they wanted to remove. So they had high levels of H2S, ammonia, VOCs, as well as reduced sulfur compounds. So they needed a higher airflow, but the pressure drop had to be lower and you need a compact design, as you can see here. So this particular solution was it was 3 V-bank systems and had 4 different chemisorbent medias in 4 different chambers for that. Worked out very well, and as you can see, in some cases, it's not all about having the same cookie cutter design where you may need to be creative and come up with a great design. Then ultimately, you want to take out all the odor. This is a great example of H2S brought a lot of friends along with them on this one. Ammonia, you don't really see it very often with H2S, with VOCs and reduced sulfur compounds. It was quite a bit. It was a large party that we had to accommodate, for that particular application, and worked out well. Here is a great example of how to use radial flow systems for application, where these at a plant and the horizontal footprint of a V-bank would not work. It's just too much space for what they needed. So in those cases, the radial flow was a perfect solution for that. So as you can see with the ductwork and the intricacy and the space restrictions, you can see where those systems fit perfectly, right where they needed. So. All right, so now bioscrubbers. So how the bioscrubbers work. So you still have think of it as a vessel, some type of a vessel that's going to bring in the odorous air, right, primarily H2S. So that H2S is going to travel through a biological, a media that's not impregnated, but that media houses bacteria that love to eat H2S. So that air is going to pass, the H2S air is going to pass through, and those, I'm going to call them bugs, are going to eat the H2S and exhaust out. Typically, they have a great removal rate of H2S removal between 95 to 99%, but it's just really looking for H2S. So there may be some other gases that will pass through, especially if there are VOCs that are present. So, and the way the biological scrubbers work, just using water, you got fresh water, you have the bacteria that's used for H2S, you have drains as well, and that water is being pumped into the scrubber. So what it allows, it keeps a nice, moist, and happy home for the biological bacteria. So while they're enjoying, just like humans, they're enjoying, they love to eat, they want to be happy, and they enjoy their environment. There's some nutrients that are like the vitamins for the bacteria that are sprayed in, intermittently into just to keep the environment nice and hospitable for the bacteria. Now with bioscrubbers, they love humid atmosphere, and you need a constant source of food. So any application, if you're under 5 ppm, the bioscrubber may not be the best solution for that. But you get into the higher levels, 100 to 200 ppm level, that's when the biological scrubbers would make a lot of sense to use, say for example, versus a dry system. Because in those cases, those H2S levels are super high, you're gonna be changing out that dry media too frequently where it doesn't make sense. That's where a biological scrubber will come in. And then the maintenance for biological scrubbers can be a little lower as well as they're, just from the nature of the process, is using fresh water and then the bacteria. All right, so here's a two-stage biological scrubber. So same premise, where the odorous air comes in, the H2S is removed through and here we're using there's a clay media that houses the bacteria. So removing that H2S from the airstream. Then there's a second stage of carbon that's going to remove any other odors, whether it's VOCs, maybe some of the other, as a polishing medium to take those different gases out. So in essence, you're going to scrub and have total, clean air, total odor removal from that. So a few different configurations for it. It really depends on, again, footprint, any space restrictions. Is it a remote location? Maybe if this is at a pump station, it's not going to be manned, or a lift station, where these biological scrubbers can be can have some lower maintenance, but you still have to keep an eye on it. So take a look at it, and also looking at the H2S levels. In those cases, would it make sense to use a dry versus a biological? So you have to kind of look at it both ways and see kind of the capital costs versus operating costs moving forward. So types of biomedia. So depending on the vendor, you have multiple different types of biomedia. Then that's just means something that's porous, that's going to hold on to the bacteria, give it a happy home. That could be, I've seen foam blocks and sheets, lava rock, ceramic media, silica glass media, clay. It's just a whole host of different medias. And these medias typically last about 10 years before they break down. So you get some life out of it. You just have to make sure that the conditions are optimal for the biological scrubber. Because similar to human beings, if you have an application where it's, and I'll talk about that here on the next slide, this environmental conditions for a biological scrubber. If it's too hot, the bugs don't like when it's too hot. It'll make them crazy the way it makes sometimes some people crazy when it's too hot. And also doesn't like it too cold either. So it's important to kind of keep an eye on when you're sizing the scrubber, understand the conditions. Now, there are scrubbers in cold climates. It's not a problem, but as long as that's known, just make the provisions necessary for that. And that will come down to whether you have to insulate and heat trace any water lines in the tank itself, just to make sure that the bacteria still understand they have a happy environment to thrive and eat up the H2S. So required removal efficiency, 99% at the outlet. And in some cases, it may work best to have a two-stage, for that, where you have the two-stage biological, where you have the actual biological media and then maybe a polishing media. Just understanding the flow per each vessel or tower. So you're going from 6,000 CFM per range, in that range. And on the H2S levels, you need that steady source of food for the bacteria. So that is very important. So you're looking at the average H2S level, not so much the peaks, but the average needs to be consistent. Otherwise, the bacteria won't have anything to eat. And then again, just the size of the circulation is based on the airflow and the loads as well. So, okay. So wet scrubbing. So we're not similar to biological, but in this case, we're using, this drawing here is just showing just a kind of a round tower, single stage for wet scrubbing. So in most cases, we're using either like a chemical to remove the different gases, whether that's typically H2S or depending on what gas is present. So for example, we use this example for H2S. We're using this single stage, we would use sodium hydroxide, a solution, and probably a sodium hypochlorite as well, to remove the H2S from the airstream. Now, it's recommended to have maybe two-stage approach for wet scrubbing. And the main reason is using sodium hypochlorite or bleach can be pretty expensive. And the H2S will use that up pretty fast. So if you have a two-stage solution, the first stage can be the sodium hydroxide or the caustic material. So that'll remove about 70%, 80% of the H2S. So again, that's sort of like a H2S punching bag. It's going to take the heavy hit. And then you can use another stage that'll have a mixture of the sodium hypochlorite and possibly the caustic solution to kind of polish off everything else. And then possibly there's any other organics as well. So, it kind of gives you this good illustration on how that works. And then the next slide shows the two-stage application. So that would be, you got two illustrations, one top, one on the bottom, or one is the round tank configuration, and you get better chemical usage using this combination of two, it's like a two-stage system. So that allows, as I mentioned, one stage can do kind of the roughing of the H2S, while the second stage can be more polishing. Now, when it comes to design considerations, as you see, the rectangular system can be on the smaller side versus round tanks. So that's something to keep in mind when designing these systems. Is footprint is footprint important? So in that way, that could determine what would be the best system to use. So again, with the two-stage arrangement, whereas the towers are rectangular, you get that total removal there. And different tower packing materials used to spray onto, that's what captures the different gases. Okay. So, so odor control system and our selection criteria. So what's most important? So we need to know the airflow, contaminants, and the contaminant level. At least we can start with that. And then from there, that'll determine, okay, what's going to be the best technology to use for it, whether it's dry, whether it's chemical, or it's biological. Then we can consider. Then we have to consider any space restrictions and requirements as well. And in some cases, even aesthetics can be important. There was a project had in Arizona where it was, the actual site was kind of the backdrop was the mountain, so they wanted the unit painted a brown color to match the mountain, which was very unique, but that was a requirement that had to be done. So in some cases we will keep in mind those requirements as well. So efficiency and reliability are very important as well. Okay, another audience poll. All right, so which odor control technology are you most familiar with at your facility? All right, the tallies are coming in. Okay, I'm seeing 41% dry scrubbing. Okay, 24% bio scrubbing, 12% wet scrubbing, and 2% hybrid or multi-stage systems, and 22% none at the moment. So, all right, great, great breakdown. Uh, awesome. Okay, so selected odor control solutions. I want to come up with a chart to kind of give a rough idea on when we want to use different technologies. Something kind of give you a general idea. Not shown here is the wet scrubbers, but it would fall into this line, kind of back here with the bio scrubbers and using engineered absorbents as a polisher. Because with the wet scrubbers, where they come into effect, if you have really high airflows and higher odor levels, they make more sense than, say, a biological, and of course, more sense than a dry scrubber by itself. So we put this together just to kind of give an idea of airflow here in this, on this axis. Then you have H2S levels, on this axis as well. So once you're, 10 ppm, both airflows, engineered absorbents should be fantastic. Use that, come up with a great solution. Get about 20 ppm or so and a little bit higher. It's good to take a look at and see what would be the best for, best solution. In those cases, maybe a scavenger type media followed by engineered absorbent in the same system, can remove the gases that way as well. Once you start getting, more so in the 50 ppm range, higher ranges, now it makes more sense to still maybe look at the scavenger engineered absorbers, or not maybe looking at biofilter. But once you're in the 100 and up, higher airflows, from there you're looking for maybe a hybrid solution where you're using a bio scrubber, with a dry system to kind of give you an overall great odor removals, option, especially with the wet scrubbers as well, as you get to the higher airflow with the higher concentration levels of different gases. Again, another slide showing the different technologies, similar to that graph, but more of a quick, comprehensive rule of thumb. And I will say, with these different technologies, they are very compatible with each other. They're not so much competitors, they're actually friends, and they work very well together. So in some cases it makes sense. It may make sense to use maybe a dry system, even if it's low airflow, high levels may work out best for space requirements, for space restrictions. But once you have the higher airflow, higher levels, well, great. Maybe use a wet scrubber or a bio, but then follow that up with a dry system. That way you're removing all the odors and getting rid of all of H2S and his friends. And here, just going to show another example of some phenomenal teamwork from a bio scrubber and a dry system here. This project's up in Cary, North Carolina. There's a biological scrubber here. And that H2S is being eaten up, exhausted out, goes into 2 vertical tanks for the total odor removal. So again, these technologies can be married together in nice marital harmony and matrimony. Okay, so odor control technology comparison. So dry scrubbers, great, low maintenance, high efficiency. You can really customize it. May not be ideal for super high odor levels and high airflow. So you kind of take a look at it both ways and see what makes sense. Biological scrubbers, non-hazardous chemicals, really effective at high levels of H2S. You may have, it may take some time for the bugs to get acclimated to the system. So it's important to kind of look at that. In most cases, you have a polishing system that works out well. So as the biological scrubbers getting online, the polishing system can take over and during that time. Wet scrubbing, again, low footprint, great air movement, high levels of odors and high airflows. But one of the downsides, you're using a lot of hazardous chemicals for wet scrubbing, and also you're changing out that chemical every month or so. So it can be expensive as far as maintenance and dealing with that, but it does have its uses in place, for applications. And with that, that is the end of the webinar. Again, thank you everyone for joining. And I just want to see if there's any questions in the audience. Let's see. Okay, I don't see any questions yet. I see a thank you. Nope, you're most welcome. I hope it was very informative. Oh, there we go.
I see there's some questions here, Anthony. I'm happy to read them off to you if that works for you.
Yeah, I do see one that says, did you touch on which ones are better for intermittent odors? Oh, intermittent odors. I would say dry scrubbers are great for intermittent odors, and also wet scrubbers as well are great for intermittent odors. From my experience in talking with some experts. There we go. Okay, we got quite a few questions. All right. Let's see. It said, I'll just read the question. It said, will attendees receive a certificate of attendance? I think Michael D covered that, and that is a yes. I have more questions here. What standard lab sample analysis procedures would you tell the lab you want them to run on Tedlar samples for this application? Oh, okay. So typically, I always want to run any sulfur compounds as well as VOCs. So that's going to give me a good start. And this question was from Rainier Niederrest. I hope I'm pronouncing that right. If not, I apologize. So that would be some of the lab procedures I would have them run. And I can also provide the exact procedure. I don't have that in front of me, but I can provide that. But I want to know the sulfur compounds. That's going to give us the H2S as well as the sulfur compounds and the VOCs. Okay, so next question. Can you explain to us how to calculate dynamic pollutant gases concentrations versus the static concentrations? Let's see. Okay, typically, from our experience, if you have dynamic versus static concentration level, if I'm using an odor log device to determine for example, let me use H2S as an example. And this question is from Maher Hadaden. So as an example, H2S, using the odor log device, putting inside of a well, no air movement. And that odor log's telling me the odor level is 200 ppm with no air movement. Typically, once air is introduced, there's going to be some dilution. So that number will go down by a factor of 10, kind of a rough indication that way. So we would at least start from there. But as the project progresses, we would like to receive or get studies or some air samples based on actual, when there's air movement, and what are those levels? Okay. Another question, and this is from let's see then. Bear with me here. I want to make sure I put the person name. Okay, this is from Justin Ivy. And it says 99% of the time we are designing a new facility and do not have data for the components in the wastewater treatment level needed or the CFM that needs to be treated. What is the best approach for selecting and sizing the odor control system with little to no information? we could at least provide conduit, pull boxes, space, and concrete pads if needed, but understand requirements. But you needed to understand requirements. So, yeah, I have screen was moving. So in those cases, Justin, what we would do, depending on the process, we would make assumptions that, okay, we're going to see, H2S, and it's going to be some other gases there. Now, for thinking about a dry system, and of course, we don't know how much we're going to see. We can even provide calculations that if you see 1 ppm up to 10 ppm, this is how long the media would last. There's the size system you would need for each application. So we would kind of start there, make some assumptions, and we would have medias that would kind of like blends that would kind of give you an overall broad spectrum removal of different gases. So we kind of start there, say, all right, this would be the solution we will provide. Now, having that budget solution, maybe not knowing exactly what media to use, but we do know the airflow. We can figure out the airflow using that formula. We know the volume that you want to purify, the structure of the room volume. We can calculate the CFM from there, and at least start based on whether we're doing 3 air changes or 6 air changes. We give you actually a different range of different airflows based on those air changes, just to kind of get things started and what systems will be needed for that. And we can do that. And that way, at least get a general rough idea and kind of an order of magnitude on what you're going to need. All right, Justin Ivy. On lift stations, I'm not really convinced gases pass through a passive media filter more effectively than through large hatches needed to access the pumps. It is recommended for all media life cartridge style odor control, utilize a non-passive system with a fan to force air from the wet well through the media. How can you remove odor from water, potable drinking water, in a 2 million gallon tank that is already filtered and smells like chlorine? Oh, no, sorry, that was another question, sorry. All right, so Justin, to answer your question, yes, we do recommend a powered system. A lot of our systems will be powered just to actively force that air through the scrubber itself. So definitely agree there. So it just depends on the application, but most of the systems will be powered if we're moving that air through. Okay, next question is from Stefan Chan. And this is, how can you remove odor from water, potable or drinking water in a tube? So for this particular application, this webinar was just more on the air side. I apologize if I wasn't clear on that. So not so much removing odors from water, but from the airstream, which is more gas phase versus liquid phase. Okay. And I think from Sam Cole, he said, did you touch on which ones are better for intermittent odors? So dry scrubbers are great for intermittent odors, as well as wet scrubbers work well as well. It just depends on the odor levels are high, the airflow is high, you may look at a wet scrubber. If they're lower, then the dry system would be much better. Biological, not so much, because it needs a constant source of odors to be effective. And intermittent, so yes, you will look at one of the other 2 options. Could we get a copy of the slides? Absolutely. This is from Paloma Hernandez. I said, thank you. Very good presentation. Thank you, Wee Ye. There's Victor Sam. Any instances of dry scrubbing cultivating a biological layer component? I have not seen that. Just because of a lot of the chemisorbent medias that are used, we haven't had any issues with any biological layers forming on the media itself. Because a lot of the media, especially with the different chemicals, they can be antibacterial. They won't have any, won't promote any living organisms on the media itself. Okay, I got a question from another one from Maher Hatterden again. Can you explain to us how to calculate? Oh, I already answered that. Sorry. Does Pure make types of odor control systems? This is from David Bashart. So we make the dry systems as well, and now that biological, but now that we're part of the Clean Water One family, we have we have the whole suite of odor control solutions that we can come up with, with all the systems, whether it's chemical as well as biological, two-stage, and also the dry system as well. Ethan Brown with the question. It says, how does air temperature affect bioscrubbing? So as I mentioned, the biological scrubber, they like a constant and a very happy environment. So that between that 60 degrees Fahrenheit, 120 is kind of optimal. So so that's, if it's too hot, it could cause some issues with the bugs dying off. If it's too cold, they may not perform properly. And may have some, it may reduce the efficiency. Hassan Chalmers, thank you very much for listening. Okay. Okay, so now this is from Saeed Mohammed. What about media used? Any specific parameters? So I'm assuming that is like any used media, when it's time to, once that media is used up, it is non-hazardous, non-toxic. It can be disposed of in any landfill. You just have to follow any local code from wherever your location, but it can be disposed of. Okay, this is from Deborah Beatty. Will this presentation be available online? I believe that question is yes, or answer that question is yes. This is from Jason Kystrom. He said, we use wet scrubbers with basically sodium hypochlorite and sodium hydroxide addition to a single tower. How much chemical reduction would switching to a two-stage system would expect to see? I am not sure the answer to that, but I can make sure I get you an answer. Because I don't have that answer available, but I can find out. Let's say, next question is from Donald Zukowski. What are the performance and economic trade-offs of adding lime or other chemicals directly to the wastewater versus scrubbing the air later? That's a great question. I'll also have to defer. Write this down. I will get an answer for you on that. All right, another question from Michael Negahin. I'm pronouncing that right. Can any of these methods be adopted to odors along the pipeline or other non-point sources? They can. I've seen it in some cases, but you would have to work it on an application where they would actually tap in at certain points, on a pipeline. So I have seen it done. Really, just depend on the application and kind of looking at the entire project to see what can be done there. All right, this is from Colin Welbury. How often have you been asked to verify the performance of the installed units? Like Pierre had to be done for the Ottawa installation. It's maybe 20% of the time. Thanks for the question, Colin. When they will require some performance testing, the level. Well, let me walk back a little bit. The level of performance testing required, for example, for the Ottawa project, you don't see that very often where they want that level of detail, where you have a third-party inspector come in and do the testing. So it doesn't happen very often, but when it does, it's great to make sure you have a system that's going to actually perform. So we do see performance requirements, but in most cases, they can be done typically by a factory trained technician who's on site for startup that can do some general tests as far as H2S performance, removal efficiency, as well as any dilution to threshold testing. Okay, from Justin Gonzalez. Was this your first industry choice as a mechanical engineer? It was not. I always thought I was going to get into aerospace and design airplanes and fighter jets, and that's what I wanted to do. But life led me to gas phase filtration. So I am quite happy. Actually, it's 25 years. So it's been awesome. Okay, from Chuck Swanson. Does blowdown from biological scrubbers have low pH that needs to be neutralized prior to discharging to a sewer drain? Chuck, I will have to get back to you on that one. Because usually with the, yeah, I'll have to get a firm answer for you on that and respond. Okay, this is from Zeke, Harvard. Do you have any experience or operational insight with activated sludge diffusion or other odor control processes that take advantage of existing treatment equipment to treat odors? I do not. All right. This is from Colin. We have actually a few questions, people that already left, but I'll answer them. What media for dry scrubbing is ideal for ammonia removal? So there is a media that pure air filtration has. It's called Ammoniazor. That's used for, and this is from Jason Kystrom. That's used for ammonia removal. What technique is from Kurt Robinson? What technology is best as a mobile unit, trailer mounted? In those cases, I would say, from my experience, dry systems would be great because of the compact and simple design of the systems, where you don't require a bunch of pumps and nutrient tanks and chemical feed and metering pumps to operate the systems, where you just have a scrubber sitting on the trailers. Makes it much easier for transport. Okay, do you have experience in using water concentration data as a surrogate for air load? Do not. In some cases, we work for some projects that have H2S in water and they're stripping the water, the H2S out. I just know that you could have very high levels of H2S when that happens, but not vast experience from that. Are your slides available? This is from Charles McDonald. Yes, they are. Please do provide the exact procedure by email. This is from Rainier URS. Okay. This is from Amar. Is that any online selection software to initially suggest model or equipment size? We don't at Pure Air, but I will check with our Clean Water One family as far as any software for selection for some of the other systems. Will you be able to send out PowerPoint presentations from Samuel Tubi? Yes, we can do that. What about, this is from Saeed Mohammed, what about freeboard in calculation? I will have to get back with you on that one. This is from Colin Wilburn again. For bioscrubbing, what monitoring can be done to keep track of the health of the bugs? What nutrients would be used? So for the biological scrubbers I'm familiar with, so in essence, you use the water and nutrients to spray intermittently, maybe every 10 minutes or so, just to keep the environment moist. And that's why, and in one way of determining, life, the health of the bugs is, how efficient is the system for moving the H2S. So the efficiency is dropping. I mean, something's going on in that colony that's going to cause issues. Okay, which this is from Hector Sanchez. Which system will handle peaks of H2S? So dry systems can handle peaks of H2S. Uh, they don't necessarily, we don't size it for that. You size it for the average, but it can handle peaks as well as chemical scrubbers, wet scrubbers can handle peaks as well. Biological, this depends on how high the peaks are. Maybe could cause some issues. All right, this is from Samuel Tubi. Again, we are having issues with media losing its strength. Can we change to any media that will work better in our condition? How do we go about that? Absolutely. We'd love to know more about your process. So you have my contact information. So please feel free to give me a call, and then at least we can discuss and see what you have and what we can provide and how we can provide a solution for it. And if it's something that we personally don't do, we can actually, at least steer you in the right direction for the best solution. So please feel free to give me a call, my email or telephone. Email probably be the best way to reach me. I would appreciate a copy of the slides, please. This is from Harry Muma. Absolutely. And this is which air scrubbing method tends to have the highest power demand? That's a great question. This is from James Ports. I would say it's either one of the biologicals or the biological wet scrubbers, just because of the amount of components that are used, the different pumps. You still have blowers. So I have to get a good answer for you on that for which one would be the highest, but that's something I can work on. Okay, so this is from Mason Kiefer. This is what are good sources on making assumptions on gas concentrations in new systems? I would say in some cases, talking with different consultants and understanding the process, that would kind of give us an idea whether it's, it's dewatering, headworks, looking at historical data for that. All right, looks like our time is up now. I will say all the questions that we have, we'll definitely get back, with all the questions, make sure we provide a response. And again, I wanted to thank everyone. If I haven't gotten to your question, I apologize, but we will reach back out and get that information to you and answer those questions as best we can. Again, everyone, thank you very much for your time. Sorry for my going over, but you guys have a great rest of your day, great rest of your week. Have a great weekend. And again, thank you for your time. Really appreciate it.